So we're going to keep working with log functions. We're going to take a look at some of their properties. What do they look like visually? And we're going to take a look at maybe some inverses. We have just done a bunch with bases, and we're going to see how different bases and different logs are going to work together. So first thing we're looking at is the inverses of an exponential function. And the inverse of an exponential function, well, first off, if it's going to pass the horizontal line test, then we know the inverse will also be a function. So if I have an exponential function that would have an inverse, is going to be our log function. And noticing that our exponential function base b will have a log function, and the log function's base will be b. So that's kind of something big you want to connect. Anything that has the same base, whether it's an exponential function or a log function, those two things will be inverses of each other. Okay, so with that in mind, we can take a look at these two functions, which should be inverses of each other. Noticing again, they have the same base. I have a exponential function with the base 2, and then I have a log function with a base 2. So we could see that they're inverses by just filling in this table. You could do this with a calculator, you could do this by hand. I'm plugging in a -3 for x, and if I evaluated it 2 to the -3, I would have 1/8. And again, for -2, 2 to the -2, I get 1/4. And if we keep filling this in, and again, this is something you could do on your calculator, but just so we have a visual representation of what's happening, this would be our exponential function evaluated going from -3 to +3. So knowing that these two are inverses, I should be seeing my x and y coordinates flipping. Meaning, if I know my x value is going to be 1/8, then I should see my y value, my output, should be the reverse of what we saw for our exponential function 2 to the x. So if we were to plug this in, and again, we could grab our calculators, our Inspires, and plug this in, I would in fact get a -3. So I can see that these two are inverses because my x and y's are flipping. Okay, so again, knowing they're inverses, if x is 1/4 and I'm going to evaluate our log function, I know I should get -2. And again, just to kind of show you what we're getting here, oops, I had a mistake. No, I'm good. Just to see what we're getting here, I should be able to take a look at these and say, yep, I'm just flipping values because they are inverse operations. Okay, so something that we're going to be doing a lot is we're going to be changing bases, going between that exponential function and the log function. And one really kind of handy thing is to have this memorized, how to change between log and exponential functions. So if I have that equation, y is equal to log base b of x, I know that this is true if, and only if, I can create an exponential function of that nature. So notice what's happening. We're taking the base from the log, that's our exponential base, right? Just like we set up above, those bases are the same thing. And it's going to equal our y value over here. So base 2, that y value is equal to the number from our log. Okay. So, and there's a couple of different ways we can do this. I'll try and take you through maybe 1 or 2 different ways. First way here is just trying that change of base. So our base, which is 2, is going to be raised to that y, or what it's equal to, which is x. And I'm going to set it equal to the number of the log. Okay, now going back to our Algebra 2 days, in order to solve something like this, we'd have to have common bases. So I would want to write 8 as a base 2. If I took 2 and I cubed it, that would get me 8. So now once my bases are the same, I can say, okay, bases are the same, exponents are the same. So in that case, x would be 3. Okay. Now a different way that we could solve this is by simply introducing the same base, taking your log base, raising it to your exponential base. And then since they're inverse operations, they would undo each other. So what I mean by that is if I had the same problem, log base 2 of 8, and I'm trying to figure out what is that equal to, I can do that work, but right in the problem. So I could think to myself, log base 2, change that 8 right there. Well, that's really a 2 cubed. And now I can see the log base, the exponential base, those are the same things. Since they're inverse operations, they reduce out. And then within the problem, I can see x is equal to 3. Just a different way to perhaps take a look at that. Okay, we're going to try this change of base again. So I'm going to take my log base, I'm going to raise it to that y value, what it's equal to, and set it equal to the cube or the square root of 3. If I take that square root of 3 and I take it out of the square root, that becomes 3 to the 1/2. And now I can see x is equal to 1/2. Once the bases are equal, the exponents are equal. Okay. Same kind of thing over here. Now, what I'm going to do is try that alternate method like we did with that log base 2. And I'm going to rewrite this 1/25 within this log function. So first thing I would do is I would think, well, take it out of the 25 and let's get that as a base 5. So in other words, that's like saying 5 squared. Okay, now I want to take it out of the fraction. And to remove it from a fraction, that means I'm going to take my exponent and I'm going to negate it. Now, since my log base and the number are the same, those are inverse operations, I'm able to reduce and say x is equal to -2. So again, that's that other method of doing it. Okay, going to letter D. So I'm going to do change base again. So I'm looking at 4. I'm going to raise it to the x is equal to 1. Okay, so now I have to think, well, any number raised to 0 gives me 1. So that's going to solve this equation and tell me x is 0. That's a little bit of a different problem. Okay. Same kind of thing happens over here, but if you notice, kind of like how we did letter C, I already have the bases are equal. So if the bases are equal, think about what that exponent is with the 7. It's a 1. X should be 7. But let's watch and see how that happens with the change of base. So I'm taking this 7 that's going there. I'm raising it to the x, and I'm setting it equal to 7. And again, notice that exponent is 1. So if our bases are the same, x is 1. It's just a couple of methods on how you can solve this. Okay. We're going to try one more over here. I'm going to let you try letters F, G, and H on your own. Let's skip over to letter I and take a look at how this is slightly different. Notice how it's already in that exponential form. Okay, so this is almost saying, like, now I want to go backwards and I want to think, well, where is this 10 coming from? Well, that 10, if I think of that last problem, this 10 would be coming from the log base 10. Okay, and this exponent, well, that's what the function is going to be equal to. So that means my x value is right there. That means I'm trying to solve for x. But now think about what we have. If there is no base written, that's assumed to be a base 10. So by expanding it this way, what I can see is that in this case, x is equal to 6. Okay, another way to take a look at it is, again, that base, if it's not written, is assumed to be base 10. Exponential 10, log base 10 are inverse operations and would reduce to leave you with a value of 6. Okay. Now, it's not going to change for natural logs. Natural logs work the same way. It's just we need to understand what natural logs are. Natural logs, first off, they are abbreviated with that form ln. But the big thing you want to know is your natural log is just a log, regular log, with a base e. So with that being said, all right, we still have that change of base. Now notice a natural log, this is kind of like what we did with our change of base when we had our log base 10. Natural log of x, the inverse of the natural log is going to be your exponential base e. We're going to take a look and try and solve this a couple of different ways. First way is I'm going to rewrite this natural log as log base e, just so we can see again what it looks like. So this is like saying log base e of the square root of e is equal to x. Now, if we did the same thing that we did on the back page, we would do a change of base. So I would have e raised to the x is equal to the square root of e. And if I took the square root of e out of the square root, I could see that that's e to the 1/2, leaving me x equaling 1/2. Okay. A different way that we could do this same problem is rewriting it back at the beginning. So I could take natural log and write it as e to the 1/2. Now immediately, once my natural log and e are directly next to each other like they are here, I know they're inverse operations. They reduce out, and again, that's going to leave me with x equaling 1/2. Just maybe two different ways that you could solve the same problem. That's kind of handy when we look over here. If you know that nice little trick, natural log and e are right next to each other, they cancel out, and you have your answer. Okay, if you don't, well, let's write it as log base e of e to the 5. Okay. And then if we tried to do our change of base like we did on the front of the page, now I have something that looks like e to the x is equal to e to the 5. And again, I can see now x is going to equal 5. Okay. Now, same kind of idea over here. If I know that e and natural log, once they're paired right next to each other, are inverses, that makes this problem super fast and easy. That just means x is equal to 4. Okay, if you want to try that with your exponential base, okay, writing that same problem, that looks like e to the log base e of 4. And now this is where you almost have to go backwards and say, where is all of this stuff coming from? Well, this would be coming from our e over here, log base e. This x that we have would be that exponential x. And then I can set it equal to this, which would be my log base e of 4. So now again, that's showing me now x is going to equal 4. Personally, I think knowing that e and natural log, once they're next to each other, inverses cancel out, makes the problem super fast. Okay. So now we're going to take a look at transformations. Transformations works the same as they have in the past. So if we're looking at this function, natural log of x plus 3, this plus 3 should be telling me I am shifting to the left 3. So natural logs and regular log base 10s or regular logs in general, things to keep in mind, they will always have an x-intercept at the location 1, 0. Okay? They will also be asymptotic to the y-axis. So with that in mind, if I were to graph this out, and you could check it on your calculator, this would be shifting from that intercept at 1, 0 back 3. So I'm going to go 1, 2, 3. Now, since it was asymptotic to the y-axis, that means in this case, if I go back one more at -4, I know it will be asymptotic there. So I know it's now going to have an intercept at, in this case, it's going to be -2, 0, shifting left 3, and it's still going to be asymptotic. Okay. So now, only difference here is this guy we are shifting up 2. Okay, so keep in mind, asymptotic to the y-axis. Rather than our crossing point at 1, 0, now I want to shift that up 2 units. So now my crossing point's going to be at the coordinate 1, 2. So same idea, asymptotic to the y-axis, and it's going to be constantly increasing. Okay, logs look very similar to natural logs. The only thing is a regular log log is just going to increase less fast, I guess is a way to say it, or slower. Okay, looking at this one, log -3, this is just going to be going this time to the right 3. And our x-intercepts and our asymptotic points, those are still the same. So if I'm thinking normal x-intercept would be at 1, 0, I have to move that right 3. So that's going to go 1, 2, 3. So now it's intersecting at that coordinate 4, 0. It was asymptotic to the y-axis, so that gets shifted over 3. So I got 1, 2, 3. And now again, it just has to intersect. And it increases slower. So if you can try and show perhaps a slower increase. Okay, this one's fun. So we get a vertical stretch up to, oops, I should say stretch in there. We have a reflection over both axes. So I can say over the x-axis, and as long as you know that's coming from that negative sign, and from the y-axis, but that's coming really from that negative sign. So that's kind of a lot to take in mind. So not only are we going to reflect over the x, but also over the y, and a vertical stretch. So that's going to make it a little bit steeper. So something to keep in mind, if I'm reflecting over the y-axis, now my intercept is going to be at negative 1, 0. Okay, normally it would be increasing up, but now because I'm reflecting, it's going to be it's increasing, but it's going to be going on the bottom side of the graph. Still asymptotic to the y-axis. So we're going to have something that's going to kind of look like that. And again, things you can double check in your graphing calculator. So I'm going to stop this video here, and we're going to make this a 2-part video. Your second part I will have on YouTube, and I'm just going to label that part 2.